Okay, I must have some speedy person who can give me the y(1) range values. Y(1) range values from top to bottom. Help me out. Who's got them for me? Somebody help me out. Y(1), that's this one right here. What's the y(1) values? 1,
2, 3, 4.
Those are hard. Okay, give me the y(2) values. 5, 4, 3, 2, 1. Okay. Well, these are two equations that are, basically they're together in this table, so they are forming what we're going to call a system of equations. In other words, they have to work together. So one of our learning goals is today being able to identify solutions of systems of equations, linear systems of equations, and the other is to be able to solve linear systems of equations by graphing. So if I were to ask you, what is an ordered pair or ordered pairs that would be solutions for both of these equations, how many do you think there are? We just have a small table here. Maybe there's some more somewhere else. But do some reasoning by thinking about, well, if I did do some negative x values, if I did extend the positive x values, do I think there would be more solutions maybe? Or what do you think? Yeah? Are there any right now in our table? What would make a solution? What could even qualify as a solution for both equations? What has to be true for a solution for an equation? What does it have to do? What, Janet? What?
Satisfy both x and y.
Oh, satisfy, in other words, when you plug in the x and the y, it has to make the equation true? Okay, so then if I were to ask you then, are there any ordered pairs that would be solution to both of them? What would it have to do, that ordered pair? Have to make both of them true, right? Okay. So do you think right now, can you see any solutions right now? Hey, let's go to your graphing calculators. Let's go throw them in. It says let's verify, but we're going to apparently have to explore with it. Okay, first of all, you need to go to your y equals, and you're going to clear out anything that's in there. If any plots are turned down along the top, make sure you get up on them and press the enter key to undarken them, turn them off. And then in y(1), put your function rule x plus 1. And in y(2), put your function rule y subtract x. And then I don't want you to press the graph key, I want you to press the second graph key. I want you to find the table that the graphing calculator just made. And I want you to find that section of the table that we just completed. What's the -2? What's that? 5 minus x. Oh. It's right there already. You just have to put the function rule in, 5 minus x. Second graph takes you to the table, and I want you to find in the table the x values 0 through 4. And I want you to verify that we have a good table filled out here, first of all. Okay, and right now you're saying that this part of the table you're saying does not provide a solution for us. Is that what I'm hearing? But maybe it's somewhere else in the table. Scroll up and down the table then and see. Go ahead, find the solution then, or maybe there is no solution to this. I don't know. You made just a small part of it, but the graphing calculator's got a huge table there for you. Maybe it'll give you away the answer. Anybody got a solution for 2 equations here yet? That if it had to make both of them true? Or in other words, an x value that when you plug it into either equation, it should do what? Give the same y value. So the same x value and same y value work in both of them. It satisfies both of them. You don't think there is one? No? Okay. Then I want you to press zoom 6. Zoom 6. Do you have a graph? What's happening? Perpendicular? Or not? Should they be perpendicular?
No, but it made an X.
They might be perpendicular because why?
The ones that are negative 1x.
Oh, and that goes opposite reciprocals? Oh, so what we did is zoom 5. Go ahead and do a zoom 5 instead then. Maybe they really are perpendicular. Like Katarina said. Are they?
Yeah.
Well, yeah, because 1 and negative 1 are opposite reciprocals of each other. So remember we talked about those being integers that if we have a slope of 1 and negative 1, we should end up with perpendicular lines. Well, then tell me something else besides the fact that these lines are perpendicular.
They have different y-intercepts.
They have different y-intercepts, okay. So is it possible then that maybe one of those y-intercepts is the solution, or both of them, or? In other words, you don't think there's any x value that produces the same y value for both equations? 2 does. Okay, what happens at 2? What's the y value for when x is 2? So Morgan's talking about right here, guys.
They're both 3.
Both y values are 3.
Yep. And negative 2 would be the same.
Do you think negative 2 would be the same? Go on your table again then, second graph. Second graph, go on your table. At negative 2 then, are both the y values the same?
No, it's
No,
not.
shoot. The thought that maybe because they're opposites that would happen, that didn't work, so. Are there any other places in that table then where they have the same y values? No. Because what's happening on the graph? What do you think?
It crosses.
They're crossing, and where are they crossing at?
350.
At order pair
2.
2, 3. At order pair 2, 3, they should be intersecting. Do you think they are? Or are we making that up?
Looks like it.
Does it look like it? Okay, press the trace key and see if you can figure it out that way. When you press the trace key, what does it do? Use this blinking cursor, right? Yeah, okay, well, take an arrow key and try and get it on the point of intersection.
It's not exactly, but it's
Not
close.
exactly. I wonder how we could figure out to get it exactly.
I can round it.
Rounds.
Hmm?
Just round it.
You just round? Okay, we can just round, sure. We could do that.
2.
Or we could tell the graphing calculator, you know what, we want you to be more precise.
Zoom.
So can we figure out how to do that maybe?
Yeah.
Okay, so here's what you're gonna do. You're gonna do second trace, and you're gonna press, go down and let's see, and we want to calculate, but we want to calculate the intersection. So you're gonna press a 5, and then you're gonna press enter, enter again. It's guessing for a little bit here, and now enter one more time. And it should give you the exact point of intersection. 2, 3. Look at that. So, what's the problem there, Katie?
Mine says 1.9.
Okay. It hasn't gone past all the guessing. It's getting closer and closer, and finally it gets there, okay? It says, oh, here's your point of intersection is ordered pair 2, 3. So do you think, but just by looking at the graph, could there possibly be any other solutions?
No.
No, because they have to share the same x and y value. We have to find the one. So how many ordered pairs do you think are solutions to both equations? 1. And what does the table show? When x is 2, y is 3, and this is for, let's start that at the beginning. For both, when x is 2, y is 3. Because these guys have to work together. So, x, y, how many unknowns is that? 2. So I wonder if, I just,
It would be the same, just like the other.
like the ones we just did for today. I wonder if, since Trevor, that's his brother, TJ over there wrote this equation, I wonder if we changed his B's to Y's, if we solve this by graphing, anybody have any predictions what might happen on the graphing
It's
calculator?
in a cross, isn't it?
Well, they're gonna cross it, where are they gonna cross at?
12.25.
At what? What was, anybody remember the answer to that one?
13.
13 what?
13.
13 nickels, and in TJ's equations here, which is the nickels, X's or Y's? The Y's, so we would have ordered pair 6 times 13 nickels. I bet, and we'll do this tomorrow, but I bet these two would intersect at that particular ordered pair, if we were right. Okay, so what does the graph show?
That intersects that.
Yeah. The lines intersect at ordered pair 2, 3. So when we have 2 or more linear equations, 2 or more, we can have 3, we can have 10, we can have however many, 2 or more, containing 2 or more variables. Good news, we're only going to work with the 2 variable ones right now. 2 or more variables working together, we call it a system. So in a system, things need to work together. So we have a system of linear equations. These equations are working together. One does not get to be independent of the other. So what are we going to call a solution to a system of equations with 2 variables? What is that ordered pair 6, 13? What is that ordered pair 2, 3? It's an, I just said it.
Solution.
It's an ordered pair. It's an ordered pair. There are 2 unknowns in it. Ordered pair, the x value and the y value. And what does that ordered pair have to do? It has to make each equation in the system true. It has to make each. So when you put an x value into all the equations in the system, it better kick out what? A y value that is
True.
the same for all of them. It better kick out a y value that is the same for all of them. And then on a graph to find, you already said this, the solution of a system, you need a point they all have in common, therefore their point of intersection. So the ones they have in common, whether it's 1, a ton, maybe not at all.
There be more than one then, if they intersect again.
Okay, how could there be more than one, Henry says? Do you think you can answer that? How do you think there would be more than one? How could there be more than one solution? Do you think there could be just like 2, or maybe there could be 10?
They only intersect one time.
They can only intersect one time, unless what?
Unless they like turn.
Unless they turn. Well, lines don't turn, there's 3, right? They don't make turns. I mean, they do the whole line turns, right? Everything, there's just one fixed point. We already talked about that with rotations. So, I guess that's something we might have to answer in this chapter also then. Can there be more than one solution? Okay, so let's go to the back side and let's start solving. You can turn that graphing calculator off if it hasn't turned itself off, because we're going to graph manually now. Okay, we're going to solve this system, y equals 3x plus 1, y equals negative x plus 5. I'm so excited that this is the system of equations we get to solve by graphing, because why?
Pretty much.
Yeah, they're in slope-intercept form, and it is so easy to pick out the slope and the y-intercept, I hardly have to think. Yes! Okay, graph those lines, you know how. And if you don't, oh my goodness, we're in trouble. Minimum of how many points?
3.
3, minimum. That means the smallest number you can make. And I'm going to tell you right now that when you are graphing systems of equations, the more points you make, the better life will be. But the minimum is, and your lines need to go all the way through the graph. I am not standing for this just through your points only, all the way through that coordinate plane. And after you're done graphing the lines, say to yourself, self, this had a positive the slope. Is my line rising from left to right?
Yes.
Yes, oh cool, I can move on now to the other one. Self, this one had a negative slope. Is my line falling from left to right? Yes. Do I have a point of intersection? I do you?
Yeah.
Okay, so I'm going to say that my solution, would you write the word solution, please? Solution. Remember, we give them as ordered pairs.
1,
1, 4, you're saying, okay? Anybody want to disagree? Ordered pair 1, 4. Okay, well, notice what it says over here. You don't have a whole lot of problems to do, but it does say what?
So
Well, how are you going to show a check problem? Well, one way would
Plug it in
be,
for the equation.
yeah, one way is algebraically. Substitute them back into your equations and see if it makes both equations true, right? Not just one. You can't play favorites. It has to make both equations true. If it doesn't, then we don't have a good solution. So we can check them algebraically, or of course we could check with the graphing calculator, but we will practice with our algebraic because you're not going to get to take these graphing calculators with you today. So I'm going to write down the equations. And by the way, when you do check problems, you always, we've already said this many times, always need to check in the original name. Well, we didn't alter their names, so of course we have the original names, and we're not probably going to mess with it. So 4 is going in for Y. What was that about? And 1's going in for X in both of them. That is not a check problem. That's the start of a check problem. I just did the what? What's that called? Plugged them in, substitution, yep. Now I have to simplify it, to evaluate it. It's not really even called solving, but we kind of loosely throw that around. 4 equals 3 times 1 is 3. Bring down my plus 1. I'm still not done. Because you should not make anybody think other than yourself. 4 equals 3 plus 1 is 4. Checks out in that one. This one says 4 equals, remember I said the negative sign can be also stated as the opposite of. What's the opposite of 1? Negative 1. So I really have here a negative 1. 4 is 4. Equals is equals. Negative 1 plus 4. 5? Oh, no, I said it wrong. Negative 1 plus 5. Okay, 4. Because it's supposed to be, or because it really is? Because it really is. Oh, you would remember how many times I told you I see check problems that are just like 10 equals 10, check, and the step above says 7 minus 2. Since when is 7 take away 2, 10? Well, when you want it to be. Okay? But when you want it. Because if they don't check out, what does that mean? It's not right. Something went wrong in your graphing, most likely, right? Most likely that's where it went. So go back and try again. Questions? Anyone? Okay, moving on, just one more practice problem then. Number 2, 3x plus y equals 4x minus 2y equals 6. What's the problem with these equations?
They're not intercepted.
They're not in slope-intercept form. What kind are they in, AJ?
Standard.
Star for you. AJ says they're in standard form. Well, standard form is good for something. What's it good for? Intercepts. If you want to use the intercepts to help you graph. So if you want to use intercepts, you could, but you still have to show me work, okay? Well, let's keep practicing this slope-intercept form thing. What are we going to do to the first equation? Subtract 3x from both sides. Well, y is now alone, and it's 4 minus 3x, which is also the same as y equals what? Negative 3x plus 4. And m equals, and b equals. That's what I want, right? Negative 3, 4. So you do whatever you want, graph now, or you can both rename and then graph them both, whatever. But here's what I'm going to have to suggest. When you're graphing these, when you have plotted the points for one of them, draw the line before you start putting more points on your graph, on your coordinate plane, because you're just going to make it kind of confusing sometimes. Not a good line, but let's hope I get away with it. This is where your skills of being able to rename an equation properly come into play and to test into. Can you really do it? Because if you can't do this, rearrange x minus 2y equals 6 into slope-intercept form. It's not going to go well, is it? So I'm going to have negative 2y equal to, I can have those two flip places. I think I'll do that. What is my new name? Devin?
Y equals 1/2 x minus 3.
Y equals 1/2 x minus 3. 3 of them, folks? A negative divided by a negative x divided by a negative 2. A negative divided by a negative is a positive. And when it's x divided by 2, that is the same as 1/2 x. And a positive 6 divided by a negative 2 is a negative 3, which we could also write as subtract 3. M equals? B equals? Negative 3. And we're ready to graph that one. Because of the way I drew my line the last time, I have a feeling that you're gonna have to give away the answer for me. The solution is 2 negative 2?
Yes.
Okay. 2 negative 2. Well, now what are you gonna do?
Check.
Check. Pick your favorite equation. No.
Both of them.
And where should you check it at?
In
In the
original
standard
equation.
form name, absolutely. You don't get to do it in the rename because you're thinking I rename them properly, and of course then when you check them in your new names, they're going to check out for you. But if you didn't rename them properly, you won't catch that. So we have to go all the way back to 3x plus y equals 4.
And x minus 2.
And what's the other one, Devin?
X minus 2y equals 6.
And you know what? It's almost nicer sometimes that it goes like this. 3 times 2 plus a negative 2 equals 4. AJ, is that enough? Can I stop there?
No.
Thanks. I like to do this, so I didn't want you to make me stop. 6 plus negative 2 is? 4. Oh, because you want it to be?
No.
Oh, because it really is. Okay. And 2, take away 2 times negative 2 equals 6. Oh, this really looks like one of those, add the opposite for some people, would be a benefit. Because we have that subtraction going on, we're going to be multiplying with a negative. Oh, you know what, sometimes that just gets us in trouble. So what do we have here? 2 plus what?
Negative.
No, 4. 2 plus 4 is? 6. Checks. Do we have a good solution? Absolutely we do. So, when you solve these, you have to do what? To get the solution. No, to get the solution, what do you have to write? You have to write an ordered pair. Write an ordered pair, and then what should you do?
Check.
Do a check problem, and then if that ordered pair doesn't check, you're gonna try again. You don't have that many problems to do. Don't whip out on me, okay? Okay, you get out a sheet of loose leaf paper. I'll give you the graphs handout here in a moment.